I promised you in the last instructional video that I would explain what's special about the word bookkeeping. It's the only word in the English language, to my knowledge, that has the feature of 3 sets of double letters in a row. O-O-K-K-E-E, bookkeeping. I don't know of another word that does. Maybe you can find one. If you can, why don't you email it to me? Because I'd surely like to know. Now, so that's the payoff for my question. If you got that on your own, congratulations. And let's take a look at something called the Atwood Machine. This is something you will probably see if you do a laboratory on gravity at school, if you get to go to school with the pandemic. If you do, wear a mask, stay well, be safe, guys and gals. Here's a pulley, and hanging on the pulley are 2 masses, a small mass and a large mass, denoted by a lowercase and uppercase letters for M. And we will, for right now, not consider the mass of the pulley, and the tension from both masses will be the same. The masses are tied together, so they move together as one. There's no stretch in the string, and we don't worry about the moment of inertia, rotation, or whatever energy is needed to get the pulley spinning. So the tension on each side is the same, the string just changes direction, and I can write the Newton's second law for both masses. So, and my point of doing this is I'm going to show you the old way, that sort of the big 4-way, and why we were so excited to spend time talking about the work energy theorem, because it allows us to do some things much, much faster once we understand how to do our bookkeeping. So for this mass, the tension, since the masses are moving this way, this is the bigger mass, so there's a movement of this mass going up and the larger mass going down. The tension minus mg is ma. F equals ma, the force. The net force is the tension minus mg. And for this puppy over here, the large mass, the mg is bigger, so mg minus the tension is capital Ma. These are Newton's second laws, and these I've drawn are the free body diagrams for the 2 masses, as they'll be referred to probably in your class. Free body diagrams are diagrams of a mass or an object and the sum of all the forces that act on them. Let's add these 2 equations. I wrote them here, one on top of the other. So notice that this is a positive t and a negative t from this guy's negative t, this guy's positive t. So when we add them, the tensions cancel, and I get capital mg minus little mg is the sum of the masses times the acceleration. Do a little factoring and division, and you'll find the acceleration of the system. It's the gravity constant g at the surface of the Earth, 9.81. We're allowed to use 10 meters per second squared in the SSAT, and it's the difference in the masses, so that the big one is first, so it's positive, and the sum of the masses on the bottom. So it's a means, the Atwood machine, of slowing down the acceleration of gravity. If the little mass is half the big mass, we get m minus half of m over 3/2 m. And the m's all cancel. We get 1 minus a half, which is a half, divided by 3/2. So therefore we invert and multiply, and we get 1/3 of g. So we can go from 10 to 3.33 meters per second squared. Easier to measure on a stopwatch, which is what you would do in the lab. So there's the acceleration right there. But I would like to know what the velocities of the tied masses are. So we invoke the big 4. V final squared equals V initial squared plus 2a distance, and the distance is height. So since the initial velocity we'll assume is 0, Vf squared is just 2ah, 2hg times the difference of the masses over the sum of the masses. Take the square root of both sides and you'll get the velocity. Now all of that's well and good, but it's a lot of work. got to make the diagram, make the free body diagram, write Newton's second law twice, add them, solve, invoke the big four. It's a lot of work. So I suggest to you that our learning the work energy theorem is very important. This is just a summary of what I did before. There's the velocity squared is 2gh on our Atwood machine. But suppose we use the work energy theorem. The work done on the box plus the change in energy is the work done by the box. There is no friction. That's zero. There is no work done on the boxes. We're not touching it. Gravity is doing the work, and that is book kept inside of potential energy. So as this, we'll call each level here 0 potential energy, or we could start them at the same height if it bothers you, and you wonder, gee, why is that allowed? So we'll start the masses at the same height, and that's going to be 0 potential energy. So the change in potential energy for this block is mgh minus 0, and this is going to be negative mgh minus 0, or 0 minus mgh. It moved down, so the sign has to be the opposite. So mgh minus capital mgh plus the difference in potential energies. It started at 0, and the difference, because they're tied together, the kinetic energy is 1/2 m, all of it, v squared. So when I bring these two across the equal sign, each of their signs change, and I get capital M minus little m with g factored out, and then I multiply both sides by 2 and divide by the sum of the masses to get v squared alone, and I get 2gh m minus m over m plus m. Please notice that it is exactly the same as we got before. By noting, we wouldn't bother to write this, we would just say we know that the change in energy is 0 because we're not touching the box, so the work we do is 0. There's no friction, so the work done by the box is 0. Conservation of energy. Write the conservation of energy and solve for V. No big four, no need for free body diagrams, a much faster answer. So depending upon what you're asked to do, you will find that the work energy theorem can yield results much faster than the big four. And that is why we bother having the work energy theorem as part of our toolbox.